Objective: the second objective of this study is to investigate the velocity distribution under ice-covered flow conditions and discuss on their difference with that of the open channel flow conditions to gain a better understanding of the flow field and velocity distribution around ridge piers under different flow covers. One of the main features of the local scour phenomenon which helps river engineers to have a better perception of the deformation of riverbed is the ability to predict the incipient motion of bed material. Furthermore, the development of an armor layer in the scour hole around bridge piers is associated with incipient motion of sediment particles. Bed armoring process typically occurs in streams with non-uniform bed materials. This phenomenon occurs mainly due to selective erosion process in which the bed shear stress of finer sediment particles exceeds the associated critical shear stress for movement. Consequently, finer sediment particles are transported and leave coarser grains behind. Through this process, the coarser grains get more exposed to the flow, while the remaining finer grains get hidden among larger ones. Armor layer is also partially due to the reduced exposure of the flow with those sediments inside the scour hole zone. For the same bed sediments, Day and Rykar found that the scour depth around bridge piers with an armor layer is less than that without armor layer. Froelich stated that the thickness of the natural armor layer is up to 1 to 3 times the particle grain size of armor layer. Rodkivi and Emma found that due to the local flow structure around a pier, local scour may either develop through the armor layer and into the finer, more erodible sediment, or it may trigger a more extensive localized type of scour caused by the erosion of the armor layer itself. Suai et al. Studied clearwater scour around semi-elliptical abutments with armored beds. The results showed that for any bed material having the same grain size, with the increase in the particle size of armor layer, scour depth will decrease. The determination of the critical condition for incipient motion of sediment and the sediment transport rate are highly crucial. To study the incipient motion of sediment particle, the Shields diagram is widely accepted. It is a graph of boundary shear stress non-dimensionalized by the submerged specific weight and the mean size of the sediment particle, which is called the Shields parameter, Shields criterion, Shields number, or dimensionless shear stress, tau c, against the boundary Reynolds number, Re. According to Shields, the critical conditions in which sediment is on the verge of becoming entrained can be determined by relating the critical Shields value, tau c, and the shear Reynolds number, Re. The boundary shear Reynolds number is defined as follows. Where d is the grain size diameter, nu is the kinetic viscosity of fluid, and u is shear velocity. In this study, since the applied bed materials are composed of non-uniform natural sediment, the particle grain size is not constant. Therefore, the median grain size of non-uniform sand, D50, is used to represent the particle size for calculating the critical shear Reynolds number. The shear velocity, U, N, 1, can be determined as follows. Where cis the channel slope, re is the hydraulic radius, and g is the gravitational acceleration. The dimensionless shear stress is used to calculate the initiation of sediment motion in a fluid flow. The critical dimensionless shear stress, tau c, is defined as follows. In which rho sand rho are the mass density of sediment and water, respectively, and UC** is the critical shear velocity, UC**, that initializes the motion of the particles. In general, the theoretical prediction of the critical condition for incipient motion is based on a force or momentum balance between the destabilizing hydrodynamic drag, Fd, and lift forces, Fl, against the resisting gravitational, W, and frictional forces, Fr. Sediment particle will be moved if the applied forces overcome the resistance force. At the threshold of movement, the applied forces are just in balance with the resisting force. In other words, a sediment particle is at a state of incipient motion when the following conditions have been satisfied. In which alpha is the scour angle. The submerged weight of the particle can be given by where ρ and ρs are the density of water and sediment, respectively, and d is the sediment size in the armor layer. Apart from geometric details such as bed slope, particle exposure, and pocket geometry, accurate prediction of incipient motion requires precise knowledge of the hydrodynamic drag, Fd, and lift forces, Fl, acting on the particle. By using Yang's criteria for incipient motion, the drag force can be expressed as where Cd is the drag coefficient at velocity versus n versus is the local velocity at a distance s above the bed. The lift force acting on the particle can be obtained as, where Cl is the lift coefficient at velocity versus Meyer-Peter and Muller proposed the following equation to calculate the sediment size in the armor layer, in which d is the size of sediment in the armor layer, s is the slope of the channel, h is the depth of mean flow, k1 is the constant number equal to 0.058 when h is in m, d90 is the bed material size where 90% of the material is finer, and n is the roughness of the channel bottom or Manning's roughness. To calculate the critical bed shear velocity N, 9, which is developed based on the law of wall method can be used. The law of wall method was originally proposed by von Karman and supposed that the velocity profile in the lower portion of an open channel flow has a logarithmic distribution, in which u macron is the average cross-sectional flow velocity, ki is the von Karman's constant which is supposed to be 0.4, represents the distance from channel bed which is supposed to be depth of water, and z0 is the roughness height which is supposed to be d50 of the sediment particles. Due to the presence of UC** in both axes of the Shields diagram, Madsen and Grant introduced a new variable rather than the shear Reynolds number in the horizontal axis of the Shields diagram which is called the sediment fluid parameter, S. The sediment fluid parameter, S, can be calculated from the following equation, in which Sg represents the specific weight of sediment. The transportation process of uniform sediment has been broadly studied, and the mechanism of sediment transport has been well discussed. However, the existing knowledge for estimating the non-uniform sediment transport is still limited. Moreover, results of laboratory experiments using uniform sediment is not an appropriate representative of natural river systems since bed materials in natural riverbeds are non-uniform and composed of sediment particles with different grain sizes. During the movement process of non-uniform sediment, the coarse grains are easier to be entrained than the same particle size of uniform sediment, because they have higher probabilities to be exposed to the flow. On the other hand, a finer grain tends to be hidden beneath the coarse grains. One of the earliest researches regarding the calculation of the bed load transport rate in a non-uniform riverbed was done by Einstein. In his proposed bed load function, he used a comprehensive hiding factor to represent the interaction effects between the coarse particles and the fine particles. Ever since, several researchers have developed formulae to determine the incipient motion of non-uniform sediment mixtures. For instance, Sch et al. Studied the incipient velocity of non-uniform sediment. As pointed out by Sch et al., the incipient velocity for the coarse particles of the non-uniform sediment is less than that for same particle size of uniform sediment, and the incipient velocity for the finer particles of the non-uniform sediment is greater than that for the same particle size of uniform sediment. Plan view and side view of the experimental flume. The number of studies on the incipient motion of sediment particles is even more limited under ice-covered flow conditions. Since ice cover imposes an additional solid boundary on the flow, the incipient motion of sediment under ice-covered flow condition is different from that under open channel flow condition. Wang et al. Studied the impacts of flow velocity and water depth on the incipient motion of bed material under ice-covered condition. It was found that the deeper the flow depth under ice cover, the higher the flow velocity needed for the incipient motion of bed material. Objective. The third objective of this study is to investigate the features of incipient motion of three non-uniform sediments under ice-covered conditions and to identify the effects of flow roughness caused by ice cover on the incipient motion of non-uniform sediment based on a series of large-scale flume experiments.